Hello everyone, today I'll talk about the solution to the problem Design Circular Deque. The statement is very long, you can read it if you want, and even though it's long, because it defines all those methods, it doesn't even say how this data structure should behave. What is this circular double-ended queue, circular deque? We know that there is some parameter k that we're given, and this is the maximum capacity of the double-ended queue. And the rest of operations are just operations that we can normally do on a double-ended queue. So in essence, we have to implement a double-ended queue that can have at most k elements. Okay, so this is pretty weird. We could be just using a double-ended queue and checking its size at every step, and this is probably one solution. But since it's probably not in the spirit of the question, the idea here, what we can do, is to allocate all those k slots immediately, and then we don't have to worry about managing memory anymore. And the central trick to a solution like this is, and that's why it's called circular, if we can have at most k elements, then we can have a single array, of course, but we can imagine that the single array is a circle. This is the position 0, position 1, position, and so on. And here is position k minus 1. And the next position after position k minus 1 is position 0. So this array of k can be seen as a circle. We can use modulo, or since in this case we're only adding and subtracting 1, only incrementing and decrementing, so we can skip modulo. We can essentially take indices modulo k, and in that case we can only use this static array of k elements. And to do so, we need two pointers. The pointer to the start and the pointer to the end of our current double-ended queue. And of course, it's an implementation detail if the elements should point to the position of the last element on the given end, or to the position of the next insertion. It's probably more natural to point to the position of the next insertion. So appending at the front will append at position 0, appending at the end would append at position k minus 1. So this is exactly what we do. We have two pointers, I call them L and R, for left and right, but really on the circle there's no left and right, so one of those in a way moves left, one of those moves right. So one starts at 0 and will be incremented, one starts at k minus 1 will be decremented. We'll remember the number of free slots, and our array for storing data is of size k. And of course, as I mentioned, our indices will be taken modulo k, so that they are always valid indices into our data. So to fix an index when we only add and subtract 1, or in general when we only add and subtract values that are already between 0 and k minus 1, instead of taking modulo, which can be quite expensive, we can just see if the value is less than 0, and in that case we add k, or if it's bigger than or equal than k, then we have to subtract k. This is just a way of avoiding using modulo, and instead using just branching operations. So first, the easiest part of our interface is the isFull and isEmpty methods. And of course, for the queue to be full, there should be nothing left as free. So at first we have k free elements, free slots, so we just negate that value. So the queue is full exactly when not self-free is true, so self-free is false, and an integer is false when it's equal to 0. There are 0 free spaces, everything matches. And of course, for the queue to be empty, the number of free slots should be exactly the same as the number of slots, so the length of our internal data buffer. And again, we negate it to return true exactly when it is empty. So, and that difference is 0. So that's the easy part. And now the two sets of 3 similar operations for picking, inserting, and deleting at both ends. They are very similar, as you can see. So I'll first go through one of those and then highlight the differences in the other. So first of all, boundary checks are important. So when we want to get the front element, we do not do it if the queue is empty. If we want to delete the front element, we don't do it if the queue is empty. When we want to insert element in the front, we cannot do it if the queue is full. The same thing happens for the last element. Now, to get the front element, we know that this L pointer that moves to the left, points to the next element that would be inserted in the front. So we have to look at the previous element, so the element to the right of it, so we have to add one, and return that element. Right? So again, in our circular buffer, if this here is L, this here is R, then L is going in this direction, let's say. So you have to go one step in the opposite direction because this is the element that is currently at the front. And L is pointing to the position where the new element would go. And of course we have to remember to call our fix function to fix the coordinates to be between 0 and k minus 1. Actually, here I have I have modulo the length of data, so those modulos are unnecessary. So I go through all the trouble of actually fixing the values, and then I left modulos here. But well, mistakes happen. Here at least there are no modulos in other fixes. So yeah, those modulos are unnecessary, right? So that's why this function fix exists. And now to insert an element, we see if the queue is not full, and then we have now one fewer free spot. We remember that the L pointer points to the next position where we can insert an element on the front. So we insert that element to our data at this position. We subtract 1 from our pointer moving to the left. We have to fix it, and this is the new pointer moving to the left, and we return true. Likewise, to delete that element, we have to again, as in getFront, take one step back from the L pointer, and the new pointer becomes that one step back. So again, it was pointing here to the position where the new element would go, so now it points here and says that the element can go here. We don't have to actually erase the value of that element, because we will just overwrite it, and we cannot now return it anyhow without overwriting it, either by L or by R, because R can catch up to us and overwrite this element first. And the differences for the other pointer are very simple, because that pointer always moves in the opposite direction. Here we have +1, so for R we have -1. Here we have -1, so for R we have +1. And again here. So those are the only differences.